So in 2.3, we're going through functions. So before we can start about the formal definition, we have to talk about what a relation is. So that's a correspondence between two sets, where each element in your first set, which is called our domain, corresponds to at least one element in the second set called the range. So you have a first set of numbers or input values, and each one of them corresponds to at least one. Could correspond to more though. So that would be our relation. A function, on the other hand, is a very specific type of relation. So each element in the first set, that domain, corresponds to exactly one. So that means each input can only have one output, where a relation, the input could possibly have two outputs. So if you think of this just kind of in real life examples, if you think of a favorite color function, the input's going to be people, the output would be your favorite color. Well, there's no stopping someone from having multiple favorite colors. I could like blue and purple simultaneously. So me as an input could have two outputs. So this would just be a relation. But if you think of a height, if I input myself, I only have one height. I don't have multiple heights. You only have one height. So as you, with the input, you correspond to exactly one output. So this would be something that would be a function. So let's look at an example. We want to see, is the relation a function? So in both of these, we're just given a bunch of coordinate pairs. So the first one is the input, the second one is the output, what it corresponds to. So if we look at this, when one is the input, one is the output. When I input one again, I get 3 as an output. And this 2 doesn't ultimately matter because here, the same input leads to 2 different outputs. So this is not a function. So I can't have the same input corresponding to different outputs. It's a relation, but it's not a function. If we look at this next one, we've got 1, 1, 2, 1, 3, 1. They all have the same output, but there's unique inputs. So 1, 2, and 3 are all different. So these are unique inputs. So it is a function. The outputs themselves don't matter. You just have to make sure that single input has a single output. But the output can repeat. So that'll be a special type of function when the output doesn't repeat. But we'll learn about that later. If we look at this example, here's our domain, 1, 2, and 3. And it outputs to 5 and 7. And so here, each input has a single arrow coming off of it. So every single input has one output. So yes, this is a function. Okay. Now let's think of this kind of graphically. We want to see, does the graph represent a function? So our input value is our x values. The output is the y. So if you look, regardless of this x I pick, if I see, it only hits the graph in one spot. So each one of these inputs has a single output. So this one, yes, it's a function. If I look over here though, if I pick this x value, it's going to hit our graph in 2 different y locations. So this single x value has 2 y outputs. So no, this is not a function. So this is something that's just called our vertical line test, which you've heard at this point in college algebra. You learn it in intermediate algebra as well. But this is a way to help us, if we have a graph, we can see, does it represent a function? So every single vertical line you draw can intersect the graph in no more than one point. If that happens, it's a function. If it does intersect the graph in multiple places, then it is not going to be a function. That is our vertical line test. So let's just look at a few examples of stuff that is and isn't a function. If we look at this one, so the blue is the function. No matter the vertical line you draw, it hits the blue line in one spot. So we're good. It's a function. If I look at this circle, No, if I draw this pink vertical line, I'm hitting the graph in 2 spots, not a function. Same thing over here. In this one location, I don't hit the graph, so that's not a problem. Even if I drew a line right here, it only hit that graph in 1 spot. But because I draw a line right here and it's hitting our blue graph in 2 places, this is not a function either. Okay? So when we do have a function, we have a very special way that we denote it. So it's with our function notation. So we write the y values are equal to functions of x's, to a function of x. So in this case, the output is our y, the input is our x. So y is a function of x. So you can read this as y equals f of x, but it indicates that x is the independent variable, so it's our input, and y is the dependent variable, which is our output. So let's look at an example, just getting used to evaluating a function. We've got f of x equals x squared plus 1, and we want to evaluate it at these given values. So all we want to do anytime we're evaluating a function, you replace x by whatever is in these parentheses. In this case, I'm just negating the whole thing, but I'm evaluating x at whatever is in these parentheses. So in the first case, anywhere I see an x, it gets replaced by 2. So it becomes 2 squared plus 1, which is 4 plus 1. So the function evaluated at 2 is 5. So that would tell us 2, 5 is a point on our graph. When I want the function evaluated at negative x, you've got to be careful how you input this, because it's x squared, so you get this squared. So ultimately, it actually gets rid of that minus sign. Negative x times negative x is positive x. So we just get x squared plus 1. When you have the minus sign on the outside, this is telling you to distribute the minus to everything in here. So it's negative times the function x squared plus 1. So you can distribute that out as negative x squared minus 1. Likewise here, I want to evaluate x and I want to replace it by x minus 1. So instead of x squared, I get x minus 1 squared. And then we add the 1. So then we actually square this out just by foiling, combine our like terms, and then we get f of x minus 1 becomes x squared minus 2x plus 2. In this last case, if I want to take f and evaluate it smiley face, that means I'm going to take smiley face squared and add 1 to it. So you are replacing any variable by the whole thing. So be careful, especially in these cases when you have 2 terms. X is getting replaced by this entire thing. So now we want to figure out, if I give you a function, what x values are going to work for it. What can I plug in? Is it known? Is it unknown? So that's going to be what is our domain of a function. So there's 2 ways it could be stated. It can be explicitly stated. So if I give you the function f of x equals 3x cubed minus 7x, and I tell you that x has to be greater than 4, I'm giving you those input values. But more often than not, we're not going to be given that. You're going to have an implicitly stated domain. So what that means is I'm going to give you the function, and you just have to tell me what values of x are okay. So if I give the function f of t is 4t divided by t plus 3, we'd have a problem when t equals negative 3, because that would make this denominator equal 0, and we know we can't divide by 0. So every other value of t except negative 3 is perfectly fine to plug in here. So if the domain isn't explicitly stated, you're going to assume it's all real numbers that don't do one of 2 things. First thing it can't do is you can't divide by 0. So any value of t that doesn't cause 0 in the denominator, you're good. That's in the domain. The other thing we want to make sure is if you have an even radical, so a square root function, 4th root function, 6th root function, what's underneath the radical cannot be negative. It can be 0, but it can't be negative. So for example, like square root of negative 2, you don't get a real output, and we want real outputs for these functions. Okay? So let's go ahead and get some practice. Let's find the domain, and then we'll express that answer in interval notation. So we have the function h of x is x to the fourth minus 1. I have no radicals. I have nothing in the denominator, so there's no problematic values of x. I can take any number, raise it to the fourth power, and subtract 1. So here x can be any real number you want. So the domain for that would be negative infinity to infinity. Anything in between here is good. If we look at the function g of t equals 2 over t squared minus 4, you have a bit of a problem. So we need that denominator So if we look at the function g of t equals 2 over t squared minus 4, that bottom factors pretty nicely to t plus 2 times t minus 2. So in this case, I need to make sure that denominator does not equal to 0. So I need t plus 2 to not equal 0 and t minus 2 to not equal 0. So I get two problematic values, t equaling negative 2 and positive 2. So any value but these is going to be perfectly fine. So if we draw a number line, I'm going to have open circles at negative 2 and 2. So in interval notation, your first interval from negative infinity to negative 2 would be here. Your second interval is from negative 2 to 2, and I can't equal those endpoints. And your third interval is from 2 to infinity. Okay? So this would be our domain. If I look at f of x equals the fourth root of x minus 3, that's an even root, so I can't take an even root of a negative number. So what we need is the expression underneath the radical to be greater than or equal to 0. Then I just want to solve for values of x that satisfy it. It's just linear, so you can directly solve for x. Let's add 3x to the other side. That's going to give us 5 is greater than or equal to 3x. Go ahead and divide by 3, and we don't need to flip it because it's not a negative value. So x needs to be less than or equal to 5 over 3. So in interval notation, from negative infinity up to 5 over 3, we're good. We'll have a positive or 0 expression under that radical. Finally, if we have the cube root of 5 minus 3x, well, that doesn't make a difference. If I take the cube root of negative 1, we're good. You can absolutely have a negative value under an odd root. So here we have no problems because you can take the cube root of negative numbers perfectly fine. Cube root of negative 1 is negative 1. Cube root of negative 8 is negative 2. So there's no value of x that's going to be problematic. So our domain, again, is all real numbers. So in interval notation, that's negative infinity to infinity. Okay. Now with this, we have properties that come with specific types of functions which are going to be useful for us. So we have increasing, decreasing, and constant functions. You can be increasing on a specific interval, decreasing on a specific interval, constant, or it could be over the entire domain. So we have very specific definitions to tell us when that's going to happen, but you can think of this in terms of the graph as well. The formal definition we have for increasing over an interval is that when you have one x value is smaller than another, the yx value corresponding to each of those follows the same inequality. So the smaller x value, the smaller the y value. For decreasing, when x1 is less than x2, the function values corresponding to that flip. So the function value corresponding to the smaller x value is larger than the other. For constant, doesn't matter what two x values you pick, they're going to have exactly the same y value. So in terms of a graph, we can just kind of see what's going on here. If I want to figure out where is this thing increasing, you read a graph just like you would read normally. You go from left to right. So here, from 2 to infinity, my y values are getting larger and larger and larger and larger. So that's from 2 to infinity. We don't want to put the square brackets because you don't want to think of increasing at a specific point. It's always going to be open brackets with it. So here is where our function is increasing. If we want decreasing, I need to be falling. So as I read this graph from left to right, my y values are getting smaller and smaller. So that's from negative infinity to negative 1. And then finally, where it's constant is what's left over. Between negative 1 and 2, our graph does not change y values at all. So here is the interval where we are constant.